Today, I'm going to be looking at a problem where we titrate a weak base with a strong acid. Now, I talk about this in my main lecture in chapter 17, but I don't do a problem like this. I even assign one of these as a bonus homework problem. It's a little bit different than this one, but I do assign one that's very similar to this. But I find a lot of my students don't actually do that problem because I think they get lost. They're not sure where to start. So I'm going to do one that's similar, and hopefully that will help my students and other students who might be watching this video. Will help them to solve these problems. So let's look at the problem. The weak base that we're going to be using is trimethylamine, CH33N. I'll just refer to it as trimethylamine. We'll have 40 milliliters of the 0.150 molar trimethylamine. It's titrated with a 0.150 molar hydrochloric acid, HCl. Calculate the pH at the following volumes. So this is very similar to a problem that we have done previously that I did, 17.41. I'll put a link up here in the corner to show you where that problem is. So you can see it's very similar to this. We're going to break this down into 4 regions. We're going to do the starting point, the buffer region, the equivalence point, and beyond the equivalence point. We're going to find that the first one's going to be the starting point. The next 2 will be in the buffer region. 40 will be at the equivalence point, and then these final 2, E and F, they will be beyond the equivalence point. So let's get started. The first one, as I mentioned, is before we've added any of the HCl. So all we have is our weak base, trimethylamine. So I've set up the concentration table for trimethylamine dissociating in water to give us trimethylammonium plus hydroxide ion. Our initial concentration of the trimethylamine is 0.150 molar. Water we're going to ignore because water is the solvent. The trimethylammonium we'll put at 0. And then here for hydroxide, we're going to put that at 0 as well. This will dissociate by some amount, which we will indicate with X, 0.150 minus X, and these will be plus X. All right, if this doesn't look familiar at all, you need to go back a couple of chapters. Go back to chapter 16. Again, I'll put a thing up here in the corner to show you where you should go on that chapter 16. Okay, so now we'll write out our Kb expression. Kb is equal to the concentration of CH3NH plus, so this, times the concentration of hydroxide divided by the concentration of CH3N. Okay, and water we don't put into the expression because it's a solvent. Now I've got a list of dissociation constants, KBs, for some common weak bases. This comes straight out of our textbook for Brown and LeMay, Appendix D2. And so you'll see right here, trimethylamine is at 6.4 times 10 to the negative 5. So I'll write that down, 6.4 times 10 to the negative 5. So we'll come back over here. Now we just need to put these values in terms of X. So we'll take the equilibrium values that are in terms of X and put them into this expression. It's going to come out to X squared over 0.150 minus X. Now, in previous problems, we've looked at how do we solve this problem? We could set it up as a quadratic equation. We're going to neglect X. We're going to do the neglect X trick. Again, go back to chapter 16 if you're not familiar with the neglect X trick. But really what it says is that X is small compared to the 0.150 that we have here. And if that's small compared to this, we can just neglect it. I go through this back in chapter 16. We have a quick trick that we can use to determine if it's okay to neglect X. We just take this number, divide by our Ka or Kb, in this case Kb, so 0.150 divided by 6.4 times 10 to the negative 5. And if that number is bigger than 400, it's okay to neglect X. As you can see, definitely bigger than 400, it is okay to neglect X. All right, so now we have neglected X. All right, so I'm going to cross multiply this. We have this equation here. I'm going to cross multiply that, and that will give us X squared is equal to 0.150 times 6.4 times 10 to the negative 5. All right. And we'll multiply those out and then take the square root. So 0.150 times 6.4, 10 to the negative 5 gives us this. And then we'll take the square root of that answer. And that gives us 3.1. Oh, I want to write this as X. X is 3.1 times 10 to the negative 3 molar. All right. Now, whenever you get to the point where you have calculated X, you've done one of these and you've calculated X, go back and check your problem. We're looking for pH. I'll go back over here so you can see we're looking for pH. All right, there we go. So we're looking for pH. And since we're looking for pH, that means we need the hydronium ion concentration. So we're going to come back over here and look at our document. X is the concentration of hydroxide. Since that is the concentration of hydroxide, then we can get the POH just by taking the negative log of that number. All right, so I'm going to do negative log. All right, and then I'm going to grab that answer and then hit that. And that gives us 2.51. But that is POH. And one of the common problems that we run into, is if you're taking a multiple choice question, this is probably one of the wrong answers. We want pH, not POH. So to get the pH, we'll need to subtract this from 14. Now, again, this only works if it's at 25 degrees Celsius, but we're going to assume that this is at 25 degrees Celsius. So we'll do 14 minus the 2.51, and that gives us 11.49. Well, I want to come back over and look at this. So I'm going to show you the titration curve. So as we go through and solve each of these, I'm going to show you where we're at on the titration curve. And so where we're at is we've calculated that very first point before we've added any of our acid. Not surprisingly, because we're starting with a base, we have a very basic pH. It's well above 7 at 11.49. And so that's where we are on that. All right. So next, we want to do the calculation at 20 milliliters. Now, I already told you a little bit ago that this one is in the buffer region. So it is in the buffer region. So let me show you how we do the calculations for this. So we're at 20 milliliters. We want to get the number of moles of our base, CH3, 3N, and we want to get the number of moles of HCl. And we want to compare those numbers and see which one's bigger. Whichever one's smaller, it's going to tell us that that's the limiting reactant at that point, and that's the one we will run out of. So let's look at this. So we've got 40 milliliters was our initial amount. And again, in case you're curious, where am I getting that from? We have a 40 milliliter sample of the 0.150 molar. So we'll come back over here, 40 milliliters, and then we'll multiply that by 0.150 molar. Because I didn't convert this into liters, the number that I'm going to get for this, the number that I'm going to get for this is going to be in millimoles. So that's going to be 6.00 millimoles of CH3, 3, N. I'm going to prove to you that that's true, that I'm not just making that up. So 40 times 0.150 comes out to 6.6. So 6.00 millimoles of that. For the moles of HCl, here we're going to do 20 milliliters times 0.150 molar. And that's going to give us 3 millimoles. So 3.00 millimoles of HCl. Okay, so now what we need to do is we need to see which one's the limiting reactant. We can see very clearly that this one's the limiting reactant. I'm going to do what I call a before and after table. With a before and after table, I'll set up the equation. So let's go ahead and start with that. So CH3, 3N plus HCl. I talk about before and after tables in chapter 17. Again, I'll put a link up here in the corner that you can refer to that. And how, when to use them and how they're different than concentration tables. All right, so this is the reaction that's occurring between trimethylamine, our weak base, and our strong acid, HCl. And then this is the conjugate acid of this base, and this is the conjugate base of that strong acid. So before and after tables are a little bit different. In a before and after table, we put millimoles instead of concentrations. And so here before we have 6.00. That real quick. And then for HCl, we've got 3.00, and this we have none. And then the chloride, we don't really care about. I mean, it's there. It's not that we don't care about it. It's a spectator ion, and it doesn't contribute to the pH because it is a very weak base. We look at these numbers. Clearly, the HCl is the limiting reactant. So we'll do minus 3.00. That'll give us that. Minus 3.00. That'll give us 3.00. And then this will be plus 3.00. Now, I told you that this is a buffer solution. And the way that we know it's a buffer solution is that we have some of our weak base and our weak acid. And they're a conjugate pair. Since we have some of each of these, we can say, yes, this is a buffer. All right, and again, it's because we have some of each of those. If we don't have both, we don't have some of each, it's not a buffer. So it will not be a buffer. Since it's a buffer, we can use the Henderson-Hasselbalch equation. In the Henderson-Hasselbalch equation, I'll write it out here. pH is equal to the pKa plus the log of the concentration of our base. The base in this case is the trimethylamine, so CH3, 3N, over the concentration of our acid. And our acid is the conjugate acid there, so CH3, 3NH plus. All right. So let's start with Ka. And so over here, we're going to figure out what Ka is. We know Kb because we had Kb a little bit earlier, but we want Ka. I wrote down Kb. I want Ka. So I want the Ka for this weak acid. So Ka is equal to Kw over Kb. We can do this as long as we have a conjugate pair. So 1.0 times 10 to the negative 14 is our Kw. Of course, that's only true at 25 degrees Celsius. And then our Kb, we saw a little bit earlier, was 6.4 times 10 to the negative 5. So now we're going to calculate that number. So 1 times 10 to the negative 14 divided by 6.4 times 10 to the negative 5. And that gives us 1.6. I'm gonna go ahead and put 3 sig figs here. Just you can put 1.6. You'll get a slightly different number if you do that. It's not a big deal, but there you go. 1.56 times 10 to the negative 10 is our Ka value. To get the pKa, we need to take the negative log of this number. So pKa equals negative log of 1.56 times 10 to the negative 10. Let me scoot that up because I'm in danger of going off the page here. There we go. Okay, so to do that, I'm going to do negative log, and then just go up here and grab that number, and I get 9.81. So our pKa is 9.81. So now I can come back over here and I can put that in. So 9.81. Now we need we need these concentrations. There's a little trick you can do, and that little trick is when you're doing a solution like this, if these are in the same solution, which they are, then in order to get the concentration, we need to take this 3.00 millimoles of this, 3.0 millimoles of this, and divide by the volume. That volume would be 60 milliliters, but because I'm dividing both of them by 60 milliliters, that'll cancel out. So the little trick you can do is simply to put the number of millimoles, or moles if you're calculating those, in here. For the base, it's 3.00, and for the acid, it's also 3.00. Now, if you're watching this video, you already know what this part is, hopefully, because 3 divided by 3 is 1, and log of 1, of course, is 0. If you didn't know that, you need to back up and go watch a different video. This would be outside of what you're supposed to be doing. So that means this section here is equal to 0. So that means our pH is equal to 9.81. This happens to be a special point in your titration curve where the pH is equal to the pKa. It means we're halfway to the equivalence point. Now, I want to go back to my titration curve, and we're actually going to see part of the curve now. All right, and here I've got the pH at the halfway point in 20 milliliters, and it came out to, again, 9.81 is there. I also took the liberty of calculating all of these on a spreadsheet. So I've calculated all of these all of these pHs as well. You'll even notice there's a little hiccup here, and that's because some of the assumptions that we use for the Henderson-Hasselbalch equation start to break down. Really what it means is it's not okay to neglect X, and so the calculations just get a little bit harder. It's not impossible. So that's why that one looks a little weird. All right, so now let's go back. We're going to do part C. On part C, we are going to be almost to the equivalence point. We will still be in the buffer range, but we're almost at the equivalence point. All right, so the next one is part C, and on part C, we're at 39.5 milliliters. So I'm going to come back over here. We're going to do the calculation here for 39. I've gone ahead and written this stuff out, so you don't have to watch me write that out. So 39.5 milliliters of the HCl solution, 0.150 molar. And when we multiply that out, we'll get 0.150 times 39.5. And that comes out to 5.925 millimoles of HCl. So we're going to take these two numbers and put them into our before and after table. So 6.00 millimoles for the trimethylamine. For the HCl, it's 5.925, 0 for this, and we don't really care about the chloride. Clearly, we can see the HCl is the limiting reactant here. So we're going to use up that. So minus 5.925, that'll give us 0. Minus 5.925. I know the answer to this, but I'm going to go ahead and show you. So 6 minus the 5.925, and that gives you 0.075. All right, this one's going to increase by 5.925 to give you 5.925. So, is this a buffer? Yes. So, yes, this is a buffer. All right, so since this is a buffer, we can use the Henderson-Hasselbalch equation. All right, pH is equal to the pKa. I'm going to get that Henderson-Hasselbalch equation here, so I don't have to rewrite it. pKa plus the log of the concentration of our base over the concentration of our weak acid. So our pKa, as we saw in the last part, was 9.81. Go back and look at part B if you want to see that. So 9.81 plus the log of the concentration. And rather than put the actual concentrations, I'm just going to put the numbers in. So we want the base 0.075 over the 5.925. All right. And so that gives us that particular number. That, because that's not a negative there. That's just a little thing. All right. So because this number is less than 1, that means this is going to be negative. Let me show you that. So 0.075 divided by 5.925, get this ratio. We're going to take the log of that number, and you'll see it comes out to a negative number. That negative number, we're going to round that to negative 1.90. So minus 1.90, 9.81 minus 1.90. And that gives us 7.91. All right, so we've progressed a little bit. We've gone a little bit further here in this. I'm going to go back over here. All right, so now we're at 39.5. You'll notice that in our titration curve, we've gotten to the part where we're getting close to the equivalence point. And spoiler, we're 0.5 milliliter away from the equivalence point. So we just have a little bit further to go. But you can see that the slope of this line is becoming a steeper negative slope. Right. So now we're going to do a problem that is at the equivalence point. All right, so on this next one, we're at 40 milliliters, and as I mentioned, that's going to be at the equivalence point. And I've taken the liberty of going ahead and writing out a little bit of stuff so you don't have to watch me write it. But our moles of trimethylamine is still 6.00. That's how much, 6.00 millimoles. That's how much we started with. For the moles of HCl, go ahead and write out that calculation. So 40.0 milliliters times the 0.150 molar, and that gives us 6.00 millimoles of HCl. Well, you can tell we're at the equivalence point because we have an equal amount of both the acid and the base. When we put the numbers in, we get 6.00 here, 6.00 there. Of course, we started off with none of that, and we don't care about the chloride. So 6.00, 6.00, since we're at the equivalence point, both of these are going to go to 0. And then this will increase to 6.00. Now that we have that, This is not a buffer, because remember, in a buffer, we need to have both the weak acid and its conjugate base, or the weak base and its conjugate acid, depending on how you want to look at it. So no, not a buffer. All right, so not a buffer. All right, because we don't have any of this, it can't be a buffer. That means that really all we have in solution is this trimethyl ammonium ion, the CH3,3NH+. And since that is all that's present in solution, then we need to calculate the concentration of that, and then write out an equilibrium for it, and then write out the equilibrium expression. It seems like it's a really long problem, but it's not too bad. So we'll start by writing concentration of CH3,3NH+, and we'll take that 6.00 millimoles of the CH3,3NH+. We want to divide by the number of milliliters. Again, when you're using millimoles, you need to divide by milliliters to get to molarity. Our number of milliliters, we started off with 40 and we've added 40 more, so that's going to be 80 total milliliters. When we do that calculation, we're going to get something that's not too surprising. Our concentration will have been cut in half, but let's go ahead and do it. 6 divided by 80, and that gives us 0.0750 molar. Well, now we want to set up a concentration table with trimethyl ammonium. That's our weak electrolyte now. So CH3, 3NH plus AQ plus water, liquid. It's in equilibrium with hydronium ion, because this is an acid, plus CH3, 3N, AQ. All right, sorry if that got a little bit sloppy. So we'll do our concentration table. All right, so there's our concentration table. They got a little ugly there. Our initial concentration of this is 0.0750 molar. Water we can ignore, and then these are 0. Our change in concentration, we'll do minus x, so 0.0750 minus x, and this will be plus x. All right, so we have the concentrations in terms of x. Now we need the Ka expression. Ka, it's hydronium, so products over reactants, so hydronium times the trimethylamine. And we'll divide by the trimethylammonium. We already have the Ka for this. We calculated that a little bit ago in part B. So here in part B, we calculated Ka as 1.56 times 10 to the negative 10. So I'm going to put that number in, 1.56 times 10 to the negative 10. And then now we want to put our equilibrium values in terms of x into this expression. So we'll have x times x, which is x squared, over 0.0750 minus x. Now, pause for a second and determine, is it okay to neglect x? Okay, hopefully after pausing, you were able to determine, yes, it's okay to neglect x. 0.075, and we'll divide that by this 1.56 times 10 to the negative 10. And that gives us a number definitely bigger than 400. It is okay to neglect x. So I'm going to get out my red pen of neglect. All right, so I got my red pen there. And now we'll cross multiply this. We'll get x squared. We're kind of running out of space here. 0.0750 times 1.56 times 10 to the negative 10. All right, we'll need to multiply those numbers, and then, so we'll take the product, and then we'll take the square root. So we'll do 0.075 times 1.56 times 10 to the negative 10. We get this number, and then we'll take the square root of that, and we'll get this number. And that comes out to, we'll rewrite this. X is equal to 3.4 times 10 to the 1, 2, 3, 4, 5, 6, negative 6 molar. Again, anytime you're doing a concentration table and you get to the point you've determined what X is, you need to go back and look at your table and see what X is. X is the hydronium ion concentration, and because it's the hydronium ion concentration, that means we're very close to getting our answer. So pH is going to be the negative log of that number, 3.4. Fix that. Negative log of 3.4 times 10 to the negative 6. All right, so I'll do negative log. I'm just going to go up and grab that number, and that gives us 5.47. All right, so in terms of, we'll come back over here. In terms of our problem, we are at the equivalence point. So we're at 40 milliliters, and you'll see that pH at 5.47. So it's there between about 5 and 6. So 5.47, we're right there. We are at the sharpest slope, or the largest slope, largest negative slope we're going to have. This is, if you're thinking in terms of math, this is the inflection point. If you're thinking in terms of calculus warning, if you're thinking in terms of calculus, your first derivative is going to be a minimum here, and your second derivative will be a 0. If you haven't taken calculus, don't worry about that. Don't worry. Okay, so our next one, since we've just done the equivalence point, our next point is going to be beyond the equivalence point. So for that, again, we're going to have to calculate how much of the acid we've added and how much of the trimethylamine we have started with. All right, so before we do that, just to show you where we're at, 40.5 milliliters, so we're going to use that number. I'll come back over here. I've already written out some stuff, again, to save a little bit of time on this video. So our moles of trimethylamine are 6.00, so 6.00. And then for the HCl, it's going to be 40.5 milliliters times 0.150 molar. It's going to give us a number just a little bit bigger than 6.0. So we'll do 40.5 times 0.150. And you'll see we get 6.075 millimoles of HCl. So for this, we have 6.00 for the trimethylamine, 6.075 for this, 0 for this, and we're ignoring chloride. Between these two, clearly our limiting reactant is the trimethylamine, so minus 6.00 minus 6.00. This is going to go to 0, and this will go to 0.075. This will increase by 6.00. So we do not have a buffer. So no, not a buffer. So because we don't have any of this, not a buffer. All right. That means we just need to look at how much acid do we have. Well, here we've got strong acid and weak acid. And whenever you have a solution that contains a strong acid and a weak acid, you really only have to look at the concentration of the strong acid. And so that's what we're going to do, is we're going to look at what the concentration of this is. We're going to ignore the effect that this would have on the pH. It might have a small effect, like, by 0.01 pH units, but we're going to ignore that. And we're going to look strictly at the concentration due to the HCl. So we'll do concentration of HCl is 0.075 millimoles of the HCl, and then we'll divide that by the volume. Our new volume, we started with 40, we've added 40.5, so that's going to give us 80.5 milliliters. And that'll give us our concentration of the HCl. So 0.075 divided by 80.5, and that gives us 9.3 times 10 to the negative 4 molar. Since HCl is a strong acid, that's going to be the concentration of the hydronium ion. Since acids dissociate 100%, essentially 100%, that should be our concentration of the hydronium ion. So that means all we need to do is to take the negative log of that. So pH is the negative log of 9.3 times 10 to the negative 4 . All right, so negative log, make sure you get log base 10, so 9.3 times 10 to the negative 4. And that gives us 3.03 as our pH. Let's go back to our titration curve. All right, yeah, I kind of messed that up. Let's try that again. There we go. So we're at 40.5 milliliters. You can see we're clearly into the excess acid region of this titration. And when we add more acid, that pH is going to continue to decrease. All right, and we'll do that here in just a second. All right, we are on to the last part of this. So 55 milliliters of HCl. We're well beyond the equivalence point. So I'm going to come back over here. And again, I've already written out some of this. So our moles of the trimethylamine, 6.00 millimoles. That's how much we started with. Our moles of HCl, we'll do 55.0 milliliters times 0.150 molar. Multiply that out, so 0.150 times 55 milliliters. That gives us 8.25 millimoles of HCl. All right, clearly we're beyond the equivalence point, so trimethylamine is our limiting reactant, 6.00 millimoles, 8.25 millimoles, and this, of course, is 0. Chloride, we don't care about. So we're going to use up all of that trimethylamine. In fact, we already have, and then minus 6.00 for this. So that gives us 0. 2.25 wrote down the wrong number there. 2.25 millimoles of that, and then plus 6.00 millimoles of our trimethyl ammonium ion. Again, this is just like the problem before it, where we've got a strong acid and a weak acid. We're only going to pay attention to that strong acid. So HCl is going to be 2.25 millimoles of HCl divided by our volume. Our volume is going to be our initial volume, which was 40, plus the 55 milliliters that we've added here. All right. And, 55. It's 55 plus 40 milliliters. It's 95 milliliters. So I goofed that up. Let's try that again. 2.25 divided by 95 milliliters. That's going to give us, we have 3 sig figs here, so I'll do 2.37 times 10 to the negative 2 molar. So I'm kind of glad I did that. That's a fairly common mistake where you forget to add in your previous volume. So pay attention to that. That is our concentration of HCl, which means that is our concentration of hydronium ion. Since that's our concentration of hydronium ion, pH is going to be super easy. pH will be negative log of 2.37 times 10 to the negative 2. It's going to give us a pH less than 2. Let's go ahead and do that. So we'll do negative log. Go grab the number. That gives us 1.63. So we get a pH of 1.63. I'm going to come over here and show you where we're at on this. So, all right, and then that's our final point that we're going to calculate. So in doing this, hopefully I have shown you that this is not too bad of a series of calculations. I think the hardest part of this is remembering that you need to break it down and look at what situation it is. Just like in the problem that we did in chapter 17, I think it's 17.41. I will put a link up here to indicate which one I'm talking about there. Just like with that, you have to break it down into the 4 regions. And the 4 regions are the beginning, which is not really a region, it's just one point. The buffer range, which is going to be all these points between where you started and the equivalence point. That's all going to be in the buffer range. And then there's at the equivalence point, which is going to be its own calculation. And then there's beyond the equivalence point. And so we did examples of each of those. Hopefully this has helped you. If it's helped you, make sure, one, write a comment in the comment sections. I always appreciate it when people do that. Sometimes people ask questions, clarifications. Another thing that you could do that would really help is if you could hit the subscribe button. The more people who watch these videos and who are subscribed, then the more people who will get to watch them later. So have a great day.